Namaste and a warm welcome to this lecture on the mathematical foundations for machine learning. We were in the process of looking at eigenvalues and eigenvectors associated with a linear map or linear transformation, and then we said that okay, there are certain invariant directions and there could be certain invariant directions to the linear maps represented by, let us say, square matrices, and that means the vectors only get scaled by the transformation, they do not undergo any direction change and stuff, and that is what we had. In the process we were also looking at a couple of other things. We said that if you have distinct eigenvalues for a given matrix, we said that look, the eigenvectors corresponding to those distinct eigenvalues are linearly independent. We proved that, and then we said that okay, this basically comes out of the fact that okay, what are the roots of the characteristic equation of the particular matrix A associated with a linear transformation T. We said that it depends on the roots. We said that the roots could be distinct, in which case all is well. We could have roots to be repeated, in which case we had a problem. When the roots are repeated, to figure out that look, you may not get as many as eigenvectors as you probably would want, especially in case of 2 dimension, where the map was taking you from R2 to R2. We had this matrix 1 1 0 1, and that matrix had a problem in the sense that if you look at the eigenvalues for this matrix, the eigenvalues are lambda 1 is equal to 1 and lambda 2 is equal to 1, and there is only one eigen direction that this particular transformation had, the shear transformation that the matrix was basically representing the shear transformation, and the shear transformation, this was basically shear along the x1 axis or x axis, and this guy had just one invariant direction, and that is where we studied the idea of algebraic multiplicity and geometric multiplicity. We always said that the geometric multiplicity is capped on the upper side by the algebraic multiplicity, that is GM, or the geometric multiplicity is always less than or equal to the algebraic multiplicity. And we said that whenever the geometric multiplicity associated with a particular eigenvalue is less than the algebraic multiplicity of that eigenvalue, there was a problem. The eigenvalue was called a deficient eigenvalue. That means this guy does not have enough number of eigenvectors as the number of times the eigenvalue repeats. There is a problem with it, and that is exactly what we are going to address in this particular lecture. And we also said that okay, there could be real matrix for which you can end up getting complex eigenvalues, which is even more dangerous, because we are trying to look at real matrices, trying to work on, which are going to reorient real vectors, and suddenly out of nowhere you see that you can get complex eigenvalues and stuff, which is going to make life a bit more tougher. Now what we are going to do in this lecture is we are going to look at these matrices which are very nice, which says that look, for these matrices I have distinct eigenvalues, right, or on a higher dimension it could be something else. So let us just focus on 2 by 2 right now, and then we will try to look at 3 by 3 and so on, right. So what we are going to do is we are going to look at the case wherein which the say the eigenvalues associated with the 2 by 2 matrix are distinct, which means each of these guys are going to have one eigenvector associated with them. Now what are we going to do with that, and that is exactly where we get into the idea of diagonalizing a matrix. So let us look at this. So let us take up this. We started with diagonalization of a matrix, and so what we are going to do is we are going to say that look, okay, I have this linear transformation T which is going to map R2 to R2 and represented by this matrix A, represented by A. That means A is going to be a 2 by 2 matrix, and we say that this A has, let us say, 2 distinct eigenvalues and each eigenvalue has its own eigenvector. Each eigenvalue is associated with eigenvectors say u and v, and we will just make a, I will say respectively, we will make a small addition here, two distinct eigenvalues, let us call them lambda 1 and lambda 2, and lambda 1 is associated with u and lambda 2 is associated with v. Now what am I going to do now? I am just going to do this simple stuff. What is that? Let us take up this. I am going to define a matrix P, define a matrix P such that the columns of P are the eigenvectors of A. So what am I going to do? I am going to have this matrix P whose first column is the vector u, that is going to be a 2 component vector, and the second column is the vector v, which is yet another 2 component vector. Now what am I going to do? I am going to do this, I am going to look at A into P. I am going to look at A into P, which is essentially saying the transformation applied on the vectors u and v. So what is AP? It is going to be A into u and v, which is nothing but you are going to get AU to be a column vector, which is going to be this, and AV is another column vector, which is this. But I know that since u and v are the eigenvectors of A associated with say lambda 1 and lambda 2 respectively, I can write this as lambda 1 u and lambda 2 v, again a 2 by 2 matrix, which essentially can be written as the u vector, the v vector. I can do this lambda 1 0 0 lambda 2. Now what have I got? This is pretty interesting. I have this matrix A, I multiplied this matrix P, essentially I got back P and then a diagonal matrix D, right. This is the diagonal matrix D. So what do we have here? We have AP is equal to PD, where P matrix was the 2 component vectors u and v corresponding to the eigenvectors, and the diagonal matrix D was basically the diagonal matrix with diagonal elements being equal to the eigenvalues. So I have AP is equal to PD, and what is interesting is we see that u and v are 2 linearly independent vectors, therefore the rank of this matrix P is going to be 2, that means the column space associated with this matrix P is 2 dimensional. That means the matrix P is invertible, right. How is it invertible? We are going to have P is equal to, let us say this vector u1 u2, that is the u vector, and we are going to have v1 v2 to be the v vector. So determinant of P is basically u1 v2 minus u2 v1, and we saw in the previous class that the vectors u and v are associated with 2 distinct eigenvalues, say lambda 1 and lambda 2, which means these will be linearly independent. If they are linearly independent, then the determinant of P is not going to be 0, and therefore the matrix P is invertible. P inverse exists. So let us see what happens if I have P inverse existing. So what is the big deal? So I am going to write AP is equal to P D. Now what I am going to do is I am going to post multiply the left hand side and the right hand side with the matrix P inverse and see what happens. So what I am going to do? I am going to do this A P and this I am going to multiply it with P inverse and here I am going to get P D P inverse, right. Now what is P into P inverse? We know that this is identity matrix. So we are going to have this implies A is equal to P D P inverse, right, and we also have this A P is equal to P D, and now what I do is I pre multiply these two guys, the both sides of the equation with P inverse. So what am I going to have? I am going to have the following: P inverse A P is equal to P inverse P D, and we know that this is identity and identity into D is going to be D itself. So I am going to have P inverse A P is equal to the diagonal matrix D, right. A is equal to P D P inverse, this is what we call as the eigen decomposition of A. You have decomposed the matrix A into a matrix P which contains the eigenvectors, D which contains the eigenvalues as the diagonal elements with off diagonal elements being 0, and P inverse is basically again the inverse of this matrix P which contains the eigenvectors. So I probably put this properly, this is P inverse, and this P inverse A P is equal to D is basically the diagonalization of A. Right, diagonalization of A. Now let us try to give a deep look into this particular expression where I have A is equal to P D P inverse. So we will do that. I have A is equal to P D P inverse. Now what I want to do is I want to look at A squared, which is nothing but A into A, which is P D P inverse into P D P inverse, right. Now if this is the case, we know that the product of P inverse P is identity. So I am going to have this is equal to P D squared P inverse. Similarly we can find out A cube is equal to P D P inverse into P D squared P inverse, because I am writing this as A into A squared, right. I am going to write this as A into A squared. Now this again is going to become the identity matrix, this product P inverse P. So I am going to have P D cube P inverse. Therefore I can generalize this to saying any A power k, I want to look at the kth power of the matrix A, I want to compute the kth power of the matrix A, it is basically equal to P D power k P inverse, right. It is P D power k P inverse. Now what is interesting is if you want to compute the kth power, all you need to do is compute the kth power of those n elements that you have. Suppose if the matrix A were to be an n by n matrix which has n distinct eigenvalues, all that you need to do is to compute A power k, you just need to find the kth power of only those n elements which are along the diagonal of the matrix D. You already know the matrix P, you have put that as the matrix which contains the eigenvectors, and P inverse is basically the inverse of this matrix. So that is computed. So all we need to do is just take P D power k P inverse. So if you want to compute the kth power, that is the power of eigenvalues and eigenvectors. If you have eigenvalues, I mean if you have n eigenvalues for an n by n matrix, and in total you have, including the multiplicities, in total you have n eigenvectors, then you can always find A power k is equal to P D power k into P inverse, because P will be an n by n matrix where each of those n columns would correspond to the eigenvector associated with the eigenvalues, right. A power k is equal to P d power k P inverse, right. Oh, something interesting also that there is something more interesting that comes into picture. What is that? Suppose if a particular eigenvalue is deficient, that means if, let us write that, if lambda 1, lambda 2 etc. lambda n are eigenvalues such that say lambda I has algebraic multiplicity more than 1. It is more than 1 and such that the algebraic multiplicities of, let us say, let us put geometric multiplicity such that the geometric multiplicities of, let us say, lambda 1 plus gm of lambda 2 plus etc. gm of lambda I plus etc. gm of, let us say, lambda n is less than n. What do we mean by that? We took the ith eigenvalue to be lambda I, and if that fellow has more than one algebraic multiplicity and assume that this guy has fewer eigenvectors than the algebraic multiplicity, right. For example, we will just take the 2 by 2 case, consider A, consider this matrix A is equal to 1 1 0 1, here lambda 1 is equal to 1 has algebraic multiplicity 2 and the eigenvector is 1 0. So, the geometric multiplicity is 1, that means lambda is equal to 1 is deficient. Lambda is equal to 1 is deficient. Now what happens? Something interesting happens. The moment you construct the matrix P, I do not have sufficient eigenvectors to get into the matrix P. I just have one eigenvector, though I have two eigenvalues, I just have one eigenvector which gets into the matrix P, which means you cannot find P inverse, which means you cannot diagonalize the matrix A. Is that clear? So, what do we mean by this? This implies P does not have, okay, the P matrix is not invertible. How? In this one case, in this previous example that we saw, I will just have the matrix P to have this vector 1 0. I mean, you can always put the other 1 0 there, but P inverse does not exist in that case, because both the column vectors are going to be the same for P, and therefore the matrix is going to be a matrix with linearly dependent columns, which means the matrix is not going to be invertible. Now, with this being the case, something happens, that means I can't find the inverse of the matrix P. If I cannot find the matrix inverse for P, I can't write this matrix A as PDP inverse, which means I can't diagonalize the matrix A. This is clear. So, that is what we said, such that if it is less than n, then we are going to say that the matrix A is not diagonalizable. This implies A cannot be written as PDP inverse, and D, the diagonal matrix, you can't get this diagonal matrix, D cannot be expressed as P inverse AP, which means the matrix A is not diagonalizable. The matrix A is not diagonalizable. So, what do we understand from here? Whenever we have geometric multiplicity of a particular eigenvalue to be less than the algebraic multiplicity, it makes the eigenvalue a deficient eigenvalue, which leads to a matrix A not being diagonalizable. Is this clear? That means you do not have an eigenvector matrix which is invertible. Therefore, you have your PDP inverse to fail. A is equal to PDP inverse to fail. This is clear. So, we are going to write this. If an eigenvalue of A, if an eigenvalue of A, say lambda 1 or say lambda, is such that the geometric multiplicity of lambda is less than the algebraic multiplicity of lambda, then A is not diagonalizable. Is this okay? When A is not diagonalizable. If it is not diagonalizable, what happens? First of all, let us understand where is this applied. Once we understand where it is applied, what are the other applications of eigenvalues and eigenvectors, we will be able to appreciate the importance of diagonalizability. Right, we will also be able to I mean we just found one application wherein which we wrote the diagonal matrix is equal to P inverse AP, and we were trying to compute the powers of A, the powers of the matrix A. It turned out to be pretty easy, because if you want to find out A squared, you would actually have to multiply with an n by n matrix with another n by n matrix, or the matrix A n by n is going to multiply with itself to give you A squared. That means, if you have an n by n matrix, you have like say n squared elements out there, and you want to multiply these n squared elements with another n squared elements out there, and you have to do a summation and all those things. There is a lot of computation that is involved. However, when you diagonalize the matrix, then you can compute the powers of A by just taking P inverse I mean PDP inverse or P d power k P inverse, where the computations are only done on those n diagonal elements. So, it is much more faster computing the powers of n elements rather than multiplying n by n matrix k times. That is going to be much more time consuming. Now, let us do one more stuff here before we get on to conclude with this particular module. The one more thing that we want to do here is recall that we started off with this idea of the eigenvectors of a matrix A corresponding to distinct eigenvalues are linearly independent, right. And we also had a case where if the eigenvalues of let us say a 2 by 2 matrix is repeated, then we figured out that there are insufficient number of eigenvalues. That means the eigenvalue was deficient, we said. Now, does this happen if you go to a higher dimensional matrix? So, if it is A 2 by 2 with repeated eigenvalues, the matrix A is not diagonalizable. I am just talking with respect to 2 by 2 matrix. So, please have that in mind, diagonalizable. Which means the eigenvalue lambda is deficient. So, the question that we have is the following question. Suppose A were 3 by 3, I have A 3 by 3 matrix, that means the transformation is going to map R 3 to R 3 itself, such that the transformation the transformation on a particular vector x is just going to scale the vector x, right. Suppose A 3 by 3 is such that number 1, it has one eigenvalue with algebraic multiplicity 3. Number 2, it has two eigenvalues lambda 1 and lambda 2 with algebraic multiplicity of lambda 1 is equal to 2 and algebraic multiplicity of lambda 2 is equal to 1. I mean, I am just looking at different conditions. So, let me put this OR. Suppose A 3 by 3 is such that it just has one eigenvalue which is repeated thrice, or it could be a matrix such that there are two eigenvalues of which one of them is repeated twice, or the third one we have such that it has 3 distinct eigenvalues. What can we say about diagonalizability in each of the cases? What can we say about diagonalizability of A in each of those cases? So, we have raised 3 important questions as far as the diagonalizability of the matrix is concerned. What we will do is we will look at the answers for these questions in the next lecture.